Afternoon, everyone, and welcome to today's seminar called Reading Annual Turbine and Varnish Reports. My name is Taylor Colon, and I am a Customer Engagement Specialist at TestOil. I'll be your host today. Before we get started, there are a few things that I want to go over. First, everyone is muted. We are recording today's presentation, and by being on mute, this will ensure a high-quality recording. Second, please feel free to use the questions box in the GoToWebinar application. We would be happy to answer any questions that you may have. Finally, the webinar recording will be distributed later today along with a survey. Look for that in the email you registered with. Let's get started with today's webinar. It's presented by Matt McMahon. In the past 18 years, Matt has reviewed over 500,000 reports as a senior data analyst at TestOil. He is a STLE certified lubrication specialist and holds degrees in automotive technology and geology. For several years, Matt has been responsible for developing and conducting the training events for TestOil. He has also hosted numerous customized webinars on oil analysis fundamentals and report interpretation. Matt has also worked on-site with many companies, helping them turn their oil analysis efforts into world-class programs. All right, and Matt, if you're ready, I will pass the controls over to you.
All right, thanks, Taylor, and welcome, everybody. Thanks for joining us this afternoon. We'll be going over these the turbine and varnish reports today, and in general, I've kind of, since we have a limited amount of time, I'm not really going to talk too much about the, the standard tests like spectroscopy and viscosity and things like that. We want to kind of focus on the tests that we only see on varnish reports and turbine reports. But we will kind of take a look at that if there's additional information that we can glean from perhaps a report that's an alarm and see if any of the other tests tell us something different. But I'm just going to really quickly just go over the look of our turbine report and our varnish report. On the screen right now is our turbine report, and like the varnish report, it's a multi-page report. Now, many years ago, we used to have a standard multi-page report for regular testing, and we transitioned to the one-page report that, if you're customers of ours right now, that you get pretty much on the routine tests. So this one, the turbine report's interesting because we have, of course, kind of a cover sheet, and then the next one, which gives the information on, what kind of machine it is it steam turbine or gas turbine? This particular one is listed as a steam turbine. And we'll have our problems and recommendations. And then on the third page is our test data summary table. A lot of times I take a look at real close look at the summary table because it's almost like a at a glance. We can take a look at it and just quickly scan to see if we have any kind of issues that stand out, especially when we have sufficient historic to kind of compare it to. But just kind of paging down through this normal report right now, we have the elemental spectroscopy, which has all of our different elements. We have viscosity, acid number, IR, we have, and then particle count, water, and then some of the things that fall under additional tests that we'll be talking about today, demossability, color, foam, RPVOT, rust. We're going to be taking a close look at those, or as much as we can in the time that we have. And then we have, of course, the varnish potential analysis group of tests, ultracentrifuge and NPC, and the ruler results. I'm just going to quickly page through this, but what's kind of unique about these two types of reports are that not only do you get like an overall problem and recommendation section on the report, but you also get detailed comments on each individual test. So it's a little unusual, we don't have those on our one page because we're kind of limited on space, but on these we go ahead and add and comment on each individual test result. So we have demossability, acid number, and we just kind of will make a quick little comment. There's usually a description followed by a comment made by the analyst. Let's take a look at a varnish report real quick. So here's our varnish report, and this one has kind of like a hybrid cover sheet. It has the sample information at the very top and then kind of a cover, and then followed at the bottom with our summary, our overall comments about the report itself. And like the turbine report, it also breaks down into individual test results and comments on each one of those. So here we have MPC. We'll be talking about that, what we call a particle count difference test. And I want to talk, I have a couple of pretty good examples that show some interesting data on those. Ultracentrifuge we'll talk about today. And then ruler, which gives us an indication of how much is in the way of antioxidants remaining in our oil. And then our regular tests like acid number, Carl Fisher water. You know, we want to include these on the varnish report because a lot of times it helps us interpret and make recommendations on what you should do. You know, you could have a situation where the degradation of the fluid is causing deposits to be formed inside the system, or it could be something else. You know, we kind of need this additional information in order to tell, in order to make those added recommendations. All right, so the first one we're going to talk about today is demulsibility. Demulsibility is a way to measure how quickly the oil separates from water. You know, this is a critical function, especially for steam turbines. And we expect these lubricants to separate fairly quickly. They shouldn't really form an emulsion layer. But it's governed by ASTM method D1401. And we take 40 milliliters of sample, 40 milliliters of water, and mix them for 5 minutes. And then we check to see how quickly it separates every 5 minutes after that. Now, for turbine oils that are, you know, like 32 or 46 viscosity, the test is only run for 30 minutes. If you send in, you know, of course you can run demulsibility on anything. It doesn't have to be just run on turbine oils, but, you know, we've had customers send in demulsibility on gear oils. If you have a thicker oil, the test actually goes for 60 minutes, and it's run at a different temperature. But we're going to kind of limit our scope here today to just turbine oils, so they run for 30 minutes. Or they can get done quicker if they have less than or equal to 3 milliliters of emulsion. So sometimes, you know, we get some of these samples in and they just don't separate. You know, you mix up the oil and the water, and you get a fairly substantial emulsion layer, get to the end of the test of 30 minutes, and you still have a substantial emulsion layer. These are some reasons why you might have poor demulsibility. You know, you might have solid particulates like carbon residue and rust. We have found that it takes very little in the way of engine oil contamination to ruin demulsibility on turbine oils. If you have a system that has a chronic water problem, it's very possible that, just like with any additive, you can deplete it over time, and when you have a lot of, you know, long-term contact with water, you may lose the demulsibility characteristics of the oil that you have in service. And we also see that as the oil is in service longer and longer and becomes oxidized, that sometimes the higher level of oxidation byproducts can start to kind of cling on to any kind of water that gets into the system, and instead of separating out, it'll tend to emulsify. So I pulled up a report right now, and I'm just taking a look at the detailed section. And here we have a sample here that says demulsibility. Our result here is 0, 30, 50 in 30 minutes. So the first number is milliliters of clear oil that we saw, followed by milliliters of clear water, and then the emulsion layer. So this has 50 milliliters of emulsion at the 30-minute mark, so that's definitely a failing result. Over in this reference column, you can kind of see that we have a passing, a 40-40-0 at 30 minutes. And historically, the previous sample on this one failed for demulsibility as well at 0.1862. So here's the detailed look. Let's take a look at the summary as a whole and see if we can spot perhaps what our issue is. So if we take a look at this one, it's kind of interesting because it appears that there's been a recent oil change. So this is at least indicating from the customer that this is a new charge of oil. And we can kind of see on the elemental spectroscopy results. Take a look at our phosphorus. You know, we're at 109, where historically we've been in the the 700, 800 range. So there is this tells me just just getting this far on the report, it tells me that this is a different oil charge than what we've seen in the past. But I think the issue on this one is this here. We have our 30 ppm calcium. A lot of times I've seen that with the reports that I've seen levels as high as 10 calcium pretty much cause failing demulsibility, and that usually indicates contamination with another product. So we'll just kind of page down and see what we have here. Evidently this is ISO grade 46. Our acid number is less than 0.2. That looks pretty good. IR doesn't really deviate much from the reference. It's clean. We have a good particle count. It's dry, although it wasn't dry last time, but it's dry this time around. However, it just doesn't separate from water. It's not dark. We have a color rating of 3, and it does a pretty good job of separating from air, but it just doesn't really separate from water too well. RPVOT is at 315. We have passing rust. These numbers look okay here for UC MPC ruler. So really we have perhaps a contamination with another product, and that's what's causing our demulsibility to fail on this particular sample. What would be our fix with this? Well, our recommendation is going to be that if you have a potential for water contamination, especially on a steam turbine, we're just going to come right out and say we recommend the oil change. Things I have seen in the past. I have seen sometimes customers send samples in with different mixtures of oils and having success that way. But I don't really, I feel like that's a hit and miss. It really depends on what the root cause of the failing demulsibility is. And I've seen where different mixtures of oils, even at the same ratio, one may pass, one may fail when you try to mix things up like that. So if you want to really fix it, I would say change out the oil. However, keep in mind, this all depends on, this is just a failing result if you get water in. If you have a system where there's no potential for water contamination, you may just want to, take that under advisement. Just consider, well, this oil doesn't really separate from water. However, the chances of water contamination are very low, and keep an eye on the other test results, but maybe this oil will be sufficient for continued service. Now, I mentioned the color test, and it ranges from a scale from 0 to 8, and on the screen right now, these actually are from, I think, 0.5 on the left all the way to this one over on the right, I think, scored a 6.5. And then it's pretty much everything in between those ranges there. But it's governed by D1500. And when I'm interpreting the reports, I just want to, if I see a radical change, and it doesn't really matter either way, right? If we have something that's really clear and now is dark, that's kind of an indication of some type of change in the system. And the other way too, right? We have, if we have a very dark color and then our recent sample is very clear and no indications of oil change, maybe it's not an indicated oil change on the report. Maybe it's a wrong sample. If it doesn't match up and there's no indication of oil change, was this identified when the sample was taken correctly, or was it taken? All right, so foam test is another one that we find on the turbine report, and it's governed by ASTM method D892. And in general, we say that it measures the foaming tendency of the lubricant. This one takes a pretty good amount of sample at 200 milliliters. So even though, when we send out these bottles for the ATA, the turbine package, they're usually gallon containers. But if we wanted to, let's say we had a sample, just a routine sample that we wanted to check, remember our 4-ounce bottles are only about 120 milliliters. So we would actually need at least 2 bottles of the 2 4-ounce bottles in order to run foam. And that's just running at once. If we want to even double check our run, now you're looking at 400 milliliters of sample. But we're purposely putting air into the sample by pushing compressed air through the diffuser stone and getting air into the sample that way. We do that for 5 minutes, and we check the volume of foam immediately after. How much foam did it generate during those 5 minutes, and then we'll monitor the amount of foam, and the test is over either at 10 minutes or when all the foam is dissipated. So a lot of times, when I'm taking a look at the reports, you got to remember we're purposely putting air into the oil, and in general, inside your machine, unless you've got a mechanical issue, which a lot of times foam tends to be, but in general, you're not purposely putting air into the oil. And you want to consider that, perhaps the dissipation time is what we're really interested in. If the oil is able to pull in air and then get rid of it, we're probably not going to have too much of a foam issue, at least in regards to the lubricant itself. Many years ago, I went to a seminar, and there was a study where they were talking about, how many, foam issues are really caused by lubricants, and it was a lot lower than I thought. A lot of times, foaming tends to be more mechanical in nature than a problem with the lubricant. That being said, as I've taken a look at turbine reports over the years, you get a lot of them that don't even, they don't even get a foam layer. You get to the end of 5 minutes, and there's no layer of foam. The test is done at that point. And then you have some that have foaming issues where you get to the end of 10 minutes and you still have the foam layer. All right, so this is what the apparatus looks like. Here's our 200 milliliter line, and here's our diffuser stone. And this is what it looks like. This one is building up a foam layer on the right side of your screen. And let's take a look at a detail and summary on a sample that's failing foam. All right, so we have this one here, and it reads 480-0448. All right, so what that means is at the end of 5 minutes of blowing, we had a foam layer of 480 milliliters. That's a lot. That's a pretty, that's a lot of foam that was generated. And it took 448 seconds for the foam to completely dissipate. Now, if we got to the 10-minute mark, we would rate here on the right side, it would be 600, because that's, 600 seconds is 10 minutes. And then we would record how much of foam layer was remaining. This one didn't make it to 10 minutes, so that middle number is 0. All right, so we got this sample, and it appears to have an issue separating from air. Let's take a look at the summary page. So here's our summary page. I'm going to just quickly go down through it. We have the elemental spectroscopy. Again, here we have this calcium. That's not really a great sign, and historically it's been in the system for a while. But otherwise, these other numbers on that spec look pretty decent. It's ISO 32. The tan is okay. And our IR doesn't look too bad here. The acid oxidation is a little bit elevated, but that's not really going to be my main focus right now. It's clean. It's dry. And here's our failing foam, 480-0448, and also take a look at, the sample not only has a problem separating from air, but it has a problem separating from water. It has a failing demulsibility, 0080. So it mixed up, 40 milliliters of water, 40 milliliters of oil, we mixed it up, and it stayed emulsified all the way to 30 minutes. So it really has an affinity to cling on the water, which is not what we want. And again, perhaps that calcium, that's very unusual, and we really shouldn't see that inside of a turbine oil, and that could indicate contamination of some sort. What would I do? I think on this one, I think I would go ahead. I would, of course, recommend an oil change, because not only are we failing foam, but we're failing demulsibility as well. Again, that's our recommendation. Maybe you take a look at the reservoir and there isn't a foam layer. Maybe there's enough time, enough residence time for those bubbles to pop. Failing demulsibility. Again, if this is a system that there's pretty much no chance of water contamination, is it a big deal? Do we want to change out the oil if there's no chance of that, and if we're taking a look at that? All right, RPVOT. Now, if you've been in this business for a while, you remember the old name of this, which was the rotating bomb oxidation test, but now it's called a rotating pressure vessel oxidation test. It's governed by D2272, and in general, it's defined as measuring the resistance to oxidation of a lubricant. Usually we use it for turbine oils, and I would say that this test doesn't really apply to some oils that are out there. I remember we had a sample sent in for RPVOT, which was a vegetable oil. It didn't have any kind of resistance to oxidation, so it didn't last that long. Consider that on some of the other lubricants that might be at your place of work. Turbine oils are unique. This is one of the things that they're formulated for, is to have a high resistance to oxidation. Gear oils and some hydraulic oils, maybe not so much. And maybe that this test doesn't really apply as well to those products if they haven't been fortified in that fashion. But in general, we want to alarm at 25% of new oil value. A lot of times I'll get questions about, hey, this new oil scored 500 on RPVOT and this other oil scored 1,000. Is this sample twice as good as the one that was at 500? And the answer is not really. You can't really compare one to the other and judge its performance. Now, I've seen samples that may not have a fantastic RPVOT, but in service they do well. I've seen other oils that score very high on RPVOT, and in service they have varnish issues. So really, you want to stay within the lubricant. You want to compare your new with your used. You don't really want to compare one lubricant to the other. It's not really meant to be that way. So we take a portion of the sample and we put it into the pressurized vessel, and we pressurize it to 90 psi, and along with the water and a copper catalyst, we'll put it into a heated bath. This is kind of like what the setup looks like. And it rotates at 100 RPM, and what tends to happen is, our antioxidants that are present in these turbine oils prevent the uptake of oxygen. So we know that, when oils oxidize, they're going to take that gaseous oxygen that's in that pressurized vessel, and they're going to convert that into like a solid. It's going to turn into acid is what it's going to do. So once that starts to happen, once we overcome the antioxidants and we start uptaking oxygen, the pressure is going to drop. And at the end of the test is defined as a drop of 25 psi from its maximum. This is a good graph. I like taking a look at this, and it's kind of interesting to look. But here's the starting point here of our test. So we pressurized it to 90 psi, and we started it here as 0 minutes. And then within dropping it in, we know that whenever we have gas, that when we heat it, it'll increase the pressure if we have a fixed volume. Well, that's what happens is we have a fixed volume, and as you can see, as it heats up, the pressure really increases. In this case, it looks like it gets to about 188, 187, somewhere around there. It hits that high point, and this really stresses out the lubricant. It's stressing out and using up the antioxidants. The antioxidants are fighting oxidation, and then at some point they are consumed, and we start reacting with the oil to make acid. And that's this big drop. Here at this point is where we've defeated the antioxidants and now are reacting. And then we record this number. Now this one here says endpoint 533 minutes. So this one made it 534 minutes before the end of the test. Is that good? Is that bad? Well, it really depends. Consider, what if this oil started off at 750? This wouldn't be that bad of a score. But if this oil was supposed to be around, 2,000, 2,000 minutes isn't unheard of. We have some samples that go 2,300, 2,500, sometimes 3,000 minutes on RPVOT. And if this was one of those products, I would be concerned because it's not reaching that point. All right, so we'll take a look at the detailed section. All right, yeah, I remember this one. So this one here, so our RPVOT is 45. That's really low. It kind of reminds me of that vegetable oil that I mentioned earlier. But 45 minutes for any turbine oil is extremely low. Whether you started at 500 or 2,000, if you're down to 45 minutes, that stuff's in pretty bad shape. And here in our detailed section, this typical new oil value for GST 32 is 1,700 minutes. Well, shoot, 1,700 minutes, 25% of that's going to be like 425 minutes. This is at 45. That's really low. Let's take a look at the summary, see what else we can find on this report. So our elemental, we have, strangely enough, we have this little peak of phosphorus. Whenever you have that, that really indicates, what do we have before? 0, 2, 0, 2, 0, 5, 25. That looks like a contamination issue, and that shouldn't really be there. Viscosity is good at 32. Look at that. Acid number, 0.39. For any of these RNO turbine oils, we really should be under this number here. We should be less than 0.2. But this one's here at 0.39, and it's been high in the past. So it's very possible that this was running, it was what we call extended service, just in place too long. Here on our IR, we even see an issue. Here our acid oxidation number is at 105. So we have high acid oxidation. Those are kind of telling the same story. It fails the emulsibility, which isn't a surprise. Remember that as our oxidation byproducts increase and things become a little bit more acidic, that we're going to have a hard time separating from water. That's what happens here. It doesn't have a foaming problem. And here's our failing RPVOT at 45. I've talked about acid oxidation and acid number, and in my regular webinar, when we talk about just regular report interpretation, I always talk about how if we have a lot of acidic components in the oil, and if we don't, whenever we do an oil change, we may not get all of that old oil out. Sometimes up to 25, 30% of that original charge is left in the system. And I always advise that once you get to a high acid number, you really got to make sure you get all of that old oil out. You probably want to perform a flush on the system. What would happen if we did it? Well, what would happen is we would drain out this system, fill it with new oil, and that acid that was left over in that oil would immediately attack our new oil, and we wouldn't realize full oil life out of it. So once we've gotten to this point, and notice, it's been like this for a while, we definitely need to flush this system out. We wouldn't just want to drain and fill. All right. Another one that we run only on the turbine test and we don't run on the varnish potential is rust. And it's used to establish the rust-preventing characteristics of a lubricant. Mainly what it's doing is it's testing for rust prevention in the presence of water. So we take a portion of the oil, mix it with water, put it into a heated bath, and immersed in the mixture that we've made is a polystyrene rod. We agitate the oil, and at the end of 4 hours, we take a look at the rod and judge it for appearance. And this is what the apparatus looks like. So on the left is the testing apparatus. So here's our beaker, and right now this one isn't filled with anything, but we would fill it with oil and water. Here's our stir bar, and then here's our polished steel rod. And then on the right side, ideally when we pull it out, the rod looks like the one on the left. But these other ones that are on the three to the right are in pretty bad shape. So with those, we would make the comment that in the presence of water, this oil doesn't really prevent corrosion. All right, so what would we do? Let's take a look at a report that has an issue. So here, it's pretty easy to see on the report. It's just going to, instead of pass, it's going to just say fail. And if we take a look at the summary on this one, elemental spectroscopy looks pretty good. It's ISO 32. Acid number is low. It's clean. It's dry. It fails the emulsibility. The foam is okay. This is just a dissipation time here. RPVOT, depending on the oil, may be all right. But here's our failing rust. Let's say that we're nowhere near an outage, and we have to go a long time before we're able to change the oil out. It's very possible that a bleed-in feed, maybe 10%, 20% of new product, may get this from a failing state into a passing state. I've seen that before. I've also seen cases where depending on the rust additive, specific rust additive, and there's many different types. There's not just one. I've seen cases where you may have a compatibility issue. You might not be having a rust problem at all, and then for some reason, your oil supplier says, hey, that product's been discontinued. We want you to use this product, and we start topping off, and lo and behold, now we get a failing rust. I've seen that happen. So, it's kind of a plug for our compatibility oil testing. Whenever we switch products, we want to make sure that they're going to get along okay. But in cases like that, if we add new product, it may work. It may go from passing to failing. But in a failing case, I would say that very possible you can go 10, 20%, and then all of a sudden get to a passing state. It wouldn't surprise me. All right, now we're going to start looking at some of our tests that focus on varnish. The first one that we're going to talk about is ultracentrifuge. So we take a portion of the sample and we spin it in an ultracentrifuge, and what happens is anything that's more dense than the oil is going to settle out to the bottom of the tube. It's not, that's the only thing that makes a difference is the density of the products. Now, what we find with in general with clean turbine oil, that what we drop out tends to be what we call insolubles. And these are a lot of times precursors to varnish issues. But keep in mind that it's anything that's more dense. What if we had a bad sample with either water or just regular dust and dirt? That would settle out as well. It doesn't really discern, but we're kind of assuming that it's a clean system, and it's going to drop out anything that's more dense than the oil itself. And this is what it looks like on your screen right now. So this one scored pretty good. As you can see, there's quite a bit of debris at the bottom of this, and let's take a look at some reports that have issues. So we haven't really taken a look at, we've looked at a lot of turbine reports, but now that we are running into tests that are shared on the varnish, we're going to look at those. All right, so I always like to start top down, already on the varnish potential critical. So I know that some of my primary indicators of insolubles are probably going to be an alarm on this report. All right, so page down, take a look at the summary. On the summary, we have MPC and particle count comparison. Okay, let's see what the report says. So here's our most recent MPC on the left side, 1895-094. It's got an MPC value of 34. Yep, that's in the critical range. It's been fairly clean in the past. Look at these previous ones. Although the sample interval is 1 year, at least with the previous one. But it looks like it was going along, and then just recently we're starting to see some issues. So let's see if we can kind of figure out what's going on with it. So we have a high MPC. All right, here's our particle count difference. So you can see on the particle count with the pore blockage, it gets a really clean score. 1311.7. Wow, that's pretty clean. And yet, when you run it on the optical particle counter, you get a very high score. It really reminds me of, many times I get questions by customers. They'll say, hey, I sent a sample to you guys, and I sent a sample to another lab, and your particle count is way lower because we normally just run pore blockage on everything that comes in here. Probably 90% or higher of the samples we run pore blockage on. We're big believers in that technology. Well, I sent it to another lab, and they got a much higher score than you did. Well, here, this is a good example of how that can happen. So we have a very clean pore blockage. We have a very dirty optical. How does, what happens? Well, as long as we don't have some type of interference like water, this is usually an indication of what we call soft particulates. So these are, again, they're kind of like varnish precursors. They kind of are, the optical particle counter can see them, but when we run the pore blockage, it actually pushes through the pores. It's soft enough to where it squeezes through. It doesn't block the pore like a hard particle would. So this is a good example of that. Here's this is the same oil, but depending on the technique that you're using for particle count, one's very clean, one's very dirty. And our assumption here is that these are soft particles. So Soft particles, again, precursors for varnish. This is kind of like strike two on this particular sample, that it's got the presence of insolubles in it. So high MPC, high difference between the methods. UC, our latest UC number here is a little bit elevated, UC of 4, and we have some deposits. So this one is really leaning towards soft deposits. All right, so we've kind of determined that. We'll take a look at the rest of this report. Okay, this is significant. Here we have a pretty good amount of antioxidants, so it's not really an oil issue. Acid number looks good. Again, it's not a degradation issue. Water is not, we only have 18 parts per million, so it's not like we're settling out a lot of water to get our high UC. And then our IR looks fairly reasonable. It matches up to what our new oil is listed for this particular sample. All right, so we have the presence of soft particulates, and our oil appears to be okay. So we're not really, we're not going to say flush on this. There's no reason to. There's no reason to get rid of the oil. But our recommendation is going to be something to the effect of, apply filtration that targets the removal of these soft particulates. It's going to be a different type of filter than what we're, that we would use just for hard particles. It's going to be some other type of setup. If we already have that in the system, we need to check to see, hey, is this working as we expected? Because we evidently have a problem with soft particulates. Let's take a look at another report. All right, varnish potential, critical. Page down, okay. MPC color value and UC value. All right, so, okay, yep. So we've always kind of had a dark patch on this one. So these are some pretty significant, here this previous one was 62, our current one's 51. Those are both critical. Let's see how this one's a little bit different. So this one, there's not much difference between the pore blockage and the optical. They're pretty close, within one ISO code. So what that tells me is the reason for our particulates are, the stuff that's getting caught are hard particulates. There's not a big difference between these two methods. All right, well that's interesting. That's a little bit different piece of data than we had on the previous report. And then when we take a look at the UC, yeah, it's dropping out a lot of material. Remember, it's just a matter of how dense is it. All it has to be is more dense than the oil, and it's going to drop out. Let's just take a look at the rest of the report before we. All right, so here's our antioxidants. Those look pretty good, 118, 66%. So antioxidant level looks great. Acid number, so we don't have an oil degradation issue, 0.02, that's good. It's dry. And, comparing to historic, because evidently we don't have a new oil reference for this particular one, but historically we haven't had that much change with the oil makeup. And I think if we keep going here, we're going to find that when we have samples that score very high on the UC, we'll go ahead and run this test called deposit classification and try to identify what those particulates are. And in this case, here we find, varnish, oxidatively derived particulates, but also we have inorganics. And this is probably what we're seeing a lot of. We're seeing a lot of probably dust and dirt, hard particulates in this sample. I'm going to page back up here. That's what this is telling us here with this particle count. We don't have that much difference. So, if it was soft particles, we would have a big difference because they would be pushing through the pores. But this one has no difference. So these are, in general, hard particulates that we're finding with both types of method here. All right. So, here our recommendation might be to check current filtration and see if there's an issue. But what I like to say a lot of times is think of particle counts as a ratio of how many particles you're getting into the oil and how many particles you're taking out. And if I just make a comment on the report and just say, yeah, change your filters or go to a different filter brand, essentially I'm only really commenting about one side of that ratio, right? I'm only really talking about the amount of particles that we pull out of the oil. I'm not really talking about how many particles are getting in. So a lot of times I like to say, check for sources of particles first. It's a lot cheaper So look for things like, faulty breathers, open hatches. Maybe we've got an issue with our new oil. Maybe we have an issue with our top-off oil. Any way that we can get particulates into the machine. Those are pretty easy problems to fix. It'd be kind of a shame if we went to a lot of effort and put a state-of-the-art filtration system when we're just dumping in particles, and that's the problem. Is the amount of aggression is high, and our filtration can't keep up with it. So do that first. Check for source of aggression before changing filters. That's my recommendation would be on this one. We've looked at a few of these already, but we'll talk about right now about membrane patch colorimetry, or MPC. And studies have found that when we catch fine insolubles, that it has a relation to the amount of varnish that may be in the system. Generally, anything over 23 is going to be an alarm. And once we make the patch, we measure it with what's called a handheld colorimeter. Now, the set of 9 patches that you see on the left side, believe it or not, the top 3 are okay. The bottom 6 are actually an alarm. So we have an issue with any of these. And notice this one on the bottom right is black. That's a little bit different issue than this varnish. This one probably has some type of a micro-diesel event where we're collapsing air bubbles and we're developing soot in the system. Let's take a look at a sample that has a high MPC. So again, varnish potential critical. And in our summary here, what do we have here? MPC and UC values indicate high level. All right. The ruler data has an issue. All right, let's look for ourselves. Yeah, so we have a history, and a lot of these are taken. Look at the times on these. They're just weeks apart instead of like a year like that other one. So 67, 69, 68, 65. Yeah, those are pretty high MPCs. 17, 15, 12, 20, 14, 11. That's not really that big of a difference, especially when you look at the 2 numbers to the right. Here we have 15, 12, 14, 11. It's a difference of 1. There's not a big difference there. Right, so what else do we have? Ultracentrifuge. Historically, within the past few weeks, we've had lots of insolubles and other things drop out to give us a high UC score. So we have high MPC, high UC, but we don't really see a difference. So that's leaning more toward hard particulates. And coming down here, we have kind of like an oddball ruler result. We have 143% amines, but 6% phenolics. Usually whenever you're over 100%, especially when you're exceeding it by this much, it's usually an indication of maybe it's not a great match to the reference that we're using. So is this some sort of oil identification issue? That's why we're getting kind of this oddball result on the ruler. I would say that if we know for sure that we haven't mixed products, we might want to send in a new reference to the lab so they can compare it to. But yeah, it's odd that you would get something over 100%. As you can see, it's always been that way. Degradation-wise, we're okay. And water, we're dry. IR, again, this is, when we look at these, it's not a real good match to our new oil. So again, when I look at this, I'm like, we definitely have some type of a oil identification issue here. It doesn't match well with the IR. It doesn't match well with the ruler. So that might just be a little bit of research we need to do. Did we tell the lab the correct oil that's in use here? But regardless of that, we definitely have with our high MPC and high UC, and a slight difference here, we do have a varnish issue. This is, again, a filtration issue. And we want to be able to filter out these insolubles so we don't stain the patch so dark. So check lube and check on filtration, see if we can get better with that. All right, I mentioned ruler, but here we'll just formally go over it. It's governed by ASTM method D6971, and it uses a technology called linear sweep voltammetry. And as you can tell from my discussion that I just had, it's really critical that we identify the oil correctly. All oils are formulated slightly different from each other, and sometimes massively different from each other. And if they don't really match up curve-wise on the ruler, you're just not going to get results that make a lot of sense. You're going to get results over 100%. That really shouldn't happen. Here is a chart that I put together. Ideally what we're looking for are these curves, and as you can see, these curves, which are indications of amount of antioxidants, over time they get lower and lower. So if we have a very pronounced curve, that's usually pretty good. We have a significant amount of antioxidants. If we have something that's kind of a flat line, that's no good. I think I have an example that we'll talk about here. Before I move on to that, though, this is kind of like what I was talking about with how it matches up. You'll notice that the shape of these curves of these two products are so different from each other. They're not the same product. There's something totally different from each other. So identification is key. If we have mixtures of oils in use, that's going to be a problem as far as ruler goes. And I would suggest, we may just want to compare the product to itself over time instead of to a virgin sample, because if it's a mixture, it's just not going to come out. Like I said, you're going to have results over 100%. You might have really low results on one of them. It's just not going to match up too well. All right, let's take a look at this particular sample. I believe this is out of a compressor. And it says here what physical properties we have a problem with. Okay, interesting. NPCs look pretty good, nice and clean. If we have, take a look at the PC, these are spot on. And neither of these would be alarmed for this particular piece of equipment. And our UC looks pretty good. Okay, that's good. So we have good MPC, no difference on the particle count, and they're both low. UC looks good at 1. All right. Ruler is 0. Okay, what's going on here? Well, here's what I'm talking about. So notice the green is our virgin oil that we're comparing it to, and the red is our in-service. And it's pretty much a flat line, which means that we've pretty much exhausted the antioxidants that were in here at one time. And of course, this is not so much of a surprise once you learn that. Here we have a really significant S number, and look at that increase. 0.5, 0.50, 0.4, 9.65. So really high. So, there's about a year in here. With regular analysis, this should have been caught before this point. But so we have an oil degradation problem. We don't really have too much of a water issue, and for a compressor, this isn't horrible at 177 parts per million. But look at here on our oxidation in the IR, 86. If this included a viscosity, I'd be willing to bet that the viscosity is very high. It's probably starting to sludge up on this. All right, so we've gone through this varnish report, and yet the problem here really isn't a varnish issue. It's more of an oil degradation issue. But that's kind of like one of the reasons why we run those additional tests, why we just don't sell, or we don't like to sell just individual, here's your MPC result, good luck trying to resolve it. We need the additional information that's on this package to kind of determine, hey, what's going on with the system? Do we have oil degradation going on that's causing these insolubles to be generated, or is it something else? All right, well, I hope you've enjoyed this. I see that we do have some questions. It's been a pleasure talking to you this afternoon. And let's see our questions. You want to read those off, Taylor?
Absolutely. Okay, the very first question we have, regarding calcium additive for high detergency oils, or if turbine in a cement plant can be ingested through the breather.
Yeah, ingress through the breather, right? Yeah, that's a good point. I bring that up a lot of times in my training sessions that, we don't want to get locked down to just a single source for some of these metals. An example that I use a lot of times is aluminum. If we take a look at the report, aluminum is generally regarded as a wear metal, or it's in the wear metal category, and yet we know that it could be contamination. What if we get a aluminum-based grease contaminating the oil? It's going to give you a high amount of aluminum. Is it a wear metal? No, it came in with the grease. Do we have a lot of external contaminants? A lot of external contaminants are made of aluminum oxides. The spec is just going to see that as aluminum. So yeah, I definitely agree with that comment. We don't want to get locked into just one explanation for the source of some of these elements.
All right, and another question here. Do you recommend additive boosters?
Okay, so I would say, generically, I would say no. I've seen a lot of those come in, and they usually, for the most part, they don't work. At least I haven't seen that many that come in through the door that we test. A lot of times I see them come in and they're separated out, or if they do separate, maybe they're not even no longer in the sample that's been given to us. And yet I know there are some success stories out there, but I would say for the most part I don't. I think I've seen issues with compatibility. I've seen issues where it just doesn't work. It just doesn't it doesn't stay in solution. I had somebody the other day ask me about, and this is somewhat related, it was engine oil. And they were talking about how they wanted to extend the life of their engine oil, and they put this ultrafiltration system on this thing, and they were like, well, we'll just, continue to add, continue to top off with new product, and that should keep my additives good. And I'm like, well, it's more than just that. It's more than just your level of additives. That the base stock that's in the oil will degrade over time, no matter what kind of additives you have. You could have antioxidants, but they get consumed. But I just brought this up to the person. I said, I don't think that's going to work too well, and I don't want you to do any damage to your machine. But again, there's a lot of different products out there. I would say for the most part, I haven't seen a lot of success stories with additives being put into in-service oils. Okay, do we got any more?
All right. Looks like there's a few more, but I think they would be best answered through email. I would like to thank everyone for joining us today, and thank you so much, Matt, for presenting.
Yep, you're welcome.